In this video, I'll discuss mass spectrometry, the discovery of isotopes, and the concept of average atomic mass. First, let me provide some historical context. Recall that at the start of the 19th century, John Dalton published a revolutionary atomic theory. Two of the statements in his theory were that all matter was made of atoms, which were indivisible, and that atoms of the same element were identical. Near the end of the 19th century, J.J. Thomson performed experiments with cathode ray tubes, leading him to discover the electron, showing that atoms have some internal structure. Part of Dalton's first statement was wrong. Atoms are, indeed, divisible. In the process of discovering and studying the electron, Thomson developed an analytical technique known as mass spectrometry. This process would lead to the disproving of Dalton's second statement regarding identical atoms. The concept behind mass spectrometry is pretty straightforward. Imagine standing on a hill and having a buddy roll a bowling ball down the hill past you. You have a hose pipe in which you spray water at the ball in an attempt to deflect its path away from you. If you have good water pressure, you'll see some deflection of the ball's path. Viewed from above, the ball's path of travel would veer away from you when it was hit by the water. What if you do the same thing, except this time your buddy rolls a tiny bouncy ball down the hill? Will this ball's path be affected more, less, or exactly the same as the larger bowling ball? The tiny bouncy ball will deflect much more. The same water pressure will have a greater effect on the lighter ball. What if a large boulder rolls down the hill? What would its path look like? The same water pressure would affect this large object less than the lighter balls. That's the exact same idea behind mass spectrometry. In a mass spec, instead of balls rolling down hills, we have ionized particles speeding through an evacuated tube. Down on this end, the stream of positive ions must pass through a strong magnetic field. This magnetic field is like the spray of water in our analogy on the previous slide. The path of particles with small masses will be deflected more by the magnetic field. Particles with large masses will be deflected less. Let's go back and look at the whole process. First, a sample of matter is injected into the mass spec and vaporized. The sample then passes through a very small opening, so small that only a few particles at a time can pass through. Next, the particles are bombarded by fast-moving electrons, which knock an electron off the particle. Our particles are now positively charged ions. The positive ions are sent through two charged plates, which greatly accelerate the particles. Then the positive ions encounter that strong magnetic field. The magnetic field bends the path of the ions. Particles with smaller masses are deflected more. Particles with larger masses are deflected less. At the end of the tube is a detector plate. The detector plate records every collision, and the mass spectrometer converts this information into a graph. The graph shows a peak at each mass where particles were detected. The height of the peak represents the quantity of collisions for that particular mass. All this occurs in a high vacuum so that the ions have a clear path through the machine. There will be no collisions with air molecules. In 1912, Thomson sent a natural sample of neon gas through a mass spectrometer. Based on Dalton's statement that atoms of the same element are always identical, Thomson expected to see one stream of neon particles hit the detector plate. Instead, he saw two. One particle with a mass of 20 and another with a mass of 22. On a modern mass spectrum, we can also observe a third very small peak at 21. Thomson came to understand that there were multiple versions of neon atoms, atoms of neon with different masses. Dalton had been wrong. Atoms of the same element are not always completely identical. Atoms of the same element with different masses came to be known as isotopes. The word isotope is Greek for at the same place. Isotopes are atoms of the same element, so they exist at the same place on the periodic table. Another way to word the definition is to say that isotopes are atoms with the same number of protons, but a different number of neutrons. Recall from the previous video that the number of protons in a nucleus defines the element. If a nucleus contains 2 protons, it's a helium atom. If a nucleus contains 6 protons, it's a carbon atom. The number of protons in an atom's nucleus is called its atomic number. The symbol Z is used to represent atomic number. The number of protons and neutrons in the nucleus of an atom is called the mass number. For example, for this helium nucleus, the atomic number is 2 because there are 2 protons present. The mass number, the total number of protons and neutrons in this particular nucleus, is 4. Every helium nucleus must have an atomic number of 2. It must have 2 protons. A helium nucleus can differ, though, in its mass number. The number of neutrons it contains can be different. We can symbolize isotopes by writing the chemical symbol for the element preceded by a superscript representing the mass number of that isotope and a subscript of the atomic number of the element. The 3 known isotopes of neon would be represented by these notations shown. Another common notation is the chemical symbol or the element name followed by the mass number of the isotope. Let's look now in more detail at a mass spectrum. The position of each peak or bar on the x-axis indicates the mass of the isotope. The y-axis reports the intensity of each peak, which is a measure of the relative abundance of each isotope. The tallest peak is arbitrarily set at 100%, and all other heights are relative to that. A mass spectrum of an element can be used to calculate the atomic mass of that element. Remember from Chem 1 that atomic mass is the average mass of the isotopes that compose that element, weighted according to the abundance of each isotope. So to calculate atomic mass from data, you need to know the mass of each isotope and its percent abundance. Looking back at this mass spectrum for neon, we have the mass of each isotope and its intensity percent. Intensity percent is not the same thing as percent abundance. We can calculate the percent abundance of each isotope from the intensity of the lines. To do this, divide the reported intensity of each peak by the total intensity of all peaks. For example, the peak at mass 20 has an intensity of 100%. We must divide this 100 by the total of the intensities of all 3 peaks, 100 plus 0.3 plus 10.2. This gives us a percent abundance of 90.5% for the neon 20 isotope. Then do the same thing for all peaks to obtain the percent abundances for those isotopes. Make sure you understand the difference between the intensity percent reported from the mass spectrometer and the percent abundance of each isotope. Always use percent abundance to calculate atomic mass. We now have all the information we need to calculate the average atomic mass of neon. We have the mass of each isotope and its percent abundance. Since the isotopes are not present in equal amounts, we have to take the weighted average. We multiply the mass of each isotope by its abundance as a decimal. The first isotope listed has a mass of 20 times its abundance as a decimal, 0.9048. For the next isotope, we multiply 21 times 0.0027. For the third isotope, 22 times 0.0925. Then add all those values together to get the average atomic mass for neon, 20.18 atomic mass units. As you just saw, we calculate the atomic mass of an element by multiplying the abundance of each isotope in decimal form by the mass of that isotope, then summing all the resulting values. One last thing I need to mention about mass spectra. Watch the label of the y-axis. On the mass spectrum we looked at, the y-axis values were the intensity percents reported by the mass spectrometer. To calculate the average atomic mass, we had to first convert from intensity percents to relative abundances. Sometimes you're lucky enough to be given the relative or the percent abundances already. You're ready to calculate the average atomic mass with the isotopic masses and the percent abundances given.